Our Sun, that bright sphere of fire that reigns over the daytime sky, may seem unique in its splendor, but in reality it is only one among the approximately 400 billion stars that inhabit the vast stellar sea that we call the Milky Way. Despite being one more in this colossal cosmic multitude, its influence on our planet is absolute and irreplaceable. It is not only about the light and heat that we perceive every day. The Sun is the vital engine that drives all the terrestrial machinery, from the formation of the winds to the swaying of the ocean currents, from the emergence of the seasons to the slightest sprout of plant life that depends on photosynthesis. Everything obeys its energy. Without its continuous presence, the Earth would be nothing more than a frozen, lifeless sphere, spinning aimlessly in the infinite darkness of the universe. And then a great question arises that has fascinated humanity since ancient times. What source of power nourishes the Sun? What is the secret behind that blinding light that travels millions of kilometers to reach us? Although it is the closest star to our planet, its interior continues to be shrouded in mysteries that defy our understanding. Throughout the decades, scientists have developed cutting-edge technology, such as specialized satellites, solar observatories, and space missions, to study it from all possible angles. However, the Sun still holds deep secrets that we are only beginning to unravel. The fascinating thing is that, despite not being able to observe its core directly, since no instrument can penetrate the intense layer of gases and plasma that covers it, we have managed to build an incredibly detailed portrait of its internal functioning thanks to the advancement of modern science. If, like me, you feel a deep fascination for the enigmas of the cosmos, I invite you to subscribe to the channel and leave your like. This way you help me share this content with many more curious people like you. Because, although it may seem impossible, science has found ingenious ways to study the invisible. Thanks to advanced computer simulations and physical theories developed over decades, astronomers can estimate with remarkable precision what happens inside this colossal stellar forge. Furthermore, by analyzing its atmosphere and the events that take place on its surface, it is possible to deduce with considerable accuracy what happens in its burning entropy. And that is precisely what we are going to discover together right now. A revealing journey into the depths of the star that gives meaning to our existence. To understand how this incandescent plasma titan is structured, it is essential to divide it into 6 fundamental regions. We will start with its outermost layers, the corona, the chromosphere, and the photosphere. Then we will delve into the inner zone, the convective region, the radiative zone, and, in the deepest part, the core. Each of these layers fulfills specific functions and manifests unique phenomena that deserve our attention. Let's start with the most distant one, the solar corona. This gaseous envelope extends millions of kilometers beyond the solar surface, projecting into space like an ethereal atmosphere. However, despite its immense size, it is practically invisible from Earth, except at a very particular moment, during a total solar eclipse. It is then, when the moon hides the intensity of sunlight, that the corona reveals itself as a bright and ghostly ring that surrounds the dark disk of the Sun, appearing like a floating jewel in the sky. It can also be detected by sophisticated instruments that capture X-ray radiation, since this region emits intensely in that spectrum. And here comes one of the most astonishing facts of all solar astrophysics. The corona is, against all logic, much hotter than the Sun's own surface, while the photosphere, the visible layer, reaches about 5,500 degrees Celsius. The corona can exceed 2 million degrees. This thermal discrepancy is baffling to science, as normally it would be expected that the temperature would decrease when moving away from the core. The most accepted explanation suggests that the solar magnetic field, in constant motion, would be releasing enormous amounts of thermal energy through phenomena known as magnetic reconnections, although this mechanism is not yet fully understood and remains the object of intense research. Descending one level, we find the chromosphere, located between the corona and the photosphere. Although its thickness barely reaches 2,000 kilometers, this thin strip is replete with dynamic activity. One of its most characteristic manifestations are spicules, columns of hot gas that emerge violently like chaotic flares, reaching heights of up to 8,000 kilometers before disappearing in just a few minutes. It is estimated that these structures move at speeds close to 20 kilometers per second, which gives an idea of the power with which they sprout from the lower layers. The chromosphere also presents a distinctive reddish hue, caused by the emission of light from hydrogen subjected to extreme temperature. The thermal conditions in this zone are around 3,700 degrees Celsius, although they increase considerably as it approaches the corona, generating an impressive thermal gradient that is not yet fully understood. And now, we go down to one of the most familiar layers, the photosphere. This is the face of the sun, the visible part that we observe from Earth, although, of course, never directly. Its name comes from Greek and means sphere of light, an accurate term, since most of the electromagnetic radiation that bathes our planet is generated here. Although it is not a solid surface like that of rocky planets, we usually refer to it as the solar surface because it is the visual limit of the star. The light that is born in the photosphere takes approximately 8 minutes to travel the 150 million kilometers that separate us from the sun, traveling at the incredible speed of 300,000 kilometers per second. The average temperature in this zone is about 5,500 degrees Celsius, and this figure serves as a reference to describe the solar temperature in general. But do not be fooled by its serene appearance. The photosphere is a place of constant agitation. Solar flares, cooler regions with intense magnetic fields, plasma eruptions, and solar storms capable of affecting even electrical grids and communication systems on Earth occur here. Although it is often imagined as a solid surface, the solar photosphere is, in reality, a thick layer of incandescent plasma, with a thickness close to 500 kilometers. Far from being firm ground, this region is more like an ocean in constant boiling, an agitated mass of ionized particles that move frantically. If a person could, in a purely hypothetical scenario, fall into it, they would not find anywhere to stand. Instead, they would immediately sink into this incandescent sea, but they would not last long. In a matter of seconds, any form of matter would be reduced to atoms by the scorching heat that dominates this zone. It is precisely here where the energy generated millions of years ago in the solar nucleus finally manages to release itself into outer space. After a slow and complex journey from the depths of the sun, the photons, those tiny particles of light, find in the photosphere their point of exit towards the universe. And it is thanks to that escape that we receive the light and heat that sustain life on Earth. This moment marks the culmination of a gigantic, silent, and invisible energetic process, but absolutely essential for everything that lives on our planet. If we observe the photosphere through specially adapted solar telescope, what we discover is a truly fascinating image, a kind of dynamic mosaic formed by luminous structures that resemble hexagonal cells, organized and in constant transformation. These figures receive the name of solar granules and are the visible expression of a physical phenomenon known as convection. In essence, they are bubbles of hot plasma that ascend from the interior, release their energy on the surface, and then descend cooled, generating a perpetual cycle of thermal movement. But that is not all. The photosphere also harbors one of the most studied phenomena of the sun, sunspots. These dark regions, which can be many times larger than the Earth, are zones where magnetic fields emerge from the inner layers, altering the local temperature and causing a significant decrease in heat. Despite their inert appearance, sunspots are in constant motion. It was by observing this displacement that astronomers managed to confirm something surprising. The sun also rotates on its axis, although at a different rate at each latitude, due to its fluid nature. And now, continuing with our immersion towards the entrails of the sun, we cross the threshold that separates the outer layers from the deepest interior. We enter the convective zone, the first of the three internal regions. Here, energy adopts a new form of transport. It no longer moves by radiation, as we will see later, but through the physical movement of the hot plasma that ascends and descends in a continuous flow. The name of this region says it all. The convective zone is called that precisely because of the dominant physical phenomenon in its interior. In its deepest parts, the temperature can reach 2 million degrees Celsius. As the plasma heats up, it becomes less dense and rises until it reaches the upper layers. There, it loses energy, cools down, and descends again, starting a new cycle. This process is very reminiscent of the bubbling that occurs when we boil water in a pot, but here, instead of steam, we are talking about enormous volumes of ionized plasma and astronomical scales. Furthermore, this region has a relatively low density compared to other solar layers, which allows greater freedom of movement for energetic particles. It is in this zone where the photons of light are finally transformed into useful heat, which will be transmitted to the photosphere and then radiated into space. But our journey does not stop here. Continuing to descend, we enter a completely different environment, where physics behaves in another way. We now arrive at the radiative zone, a region characterized by its extreme density and by a totally different method of energy transfer, pure radiation. In this region, which extends from the base of the convective zone to the very core, the photons generated by nuclear fusion begin an incredibly long odyssey. Matter is so dense in this zone that light particles cannot move in a straight line. Instead, they bounce again and again in all directions, colliding with electrons, atomic nuclei, and other particles, losing energy in each encounter. According to NASA estimates, a single photon can take more than 100,000 years to exit this region. That is to say, the light that reaches us today from the sun may have been created in its nucleus when humanity was just beginning to carve stone tools. The most astonishing thing is that, once it manages to escape from this dense and turbulent prison, that same photon will cross the remaining layers of the sun and travel the 150 million kilometers that separate it from the Earth in barely 8 minutes. That difference in times clearly illustrates the transition between an extremely oppressive environment and the vacuum of space, where the laws of motion allow extraordinary speeds. And now, yes, we arrive at the deepest and most extreme point of this entire journey, the core of the sun. This is the true engine of our star, the place where all the energy that makes it shine originate. In this stellar heart, the pressure is so colossal and the temperature so enormous, exceeding 15 million degrees Celsius, that the hydrogen atoms are forced to fuse. This process, known as nuclear fusion, transforms 4 hydrogen nuclei into a helium nucleus, releasing in the process an absolutely monumental amount of energy. It is calculated that every second, the solar core generates more energy than that produced by a billion simultaneous nuclear explosions. This energy manifests itself in the form of radiation, heat, and subatomic particles, and it is what, after a long and complex journey, finally reaches us in the form of sunlight. To give us an idea of its scale, it is estimated that the sun's core has a volume approximately 1,000 times greater than that of the Earth. But it is not only gigantic, it is also a gravitational trap. Just as photons can spend thousands of centuries trying to escape from this region, any particle trapped in the core would be condemned to remain there for entire eras. And you, if you were transported to that stellar hell, would be instantly disintegrated, and, even if by some miracle you survived, you could never leave. Because it is not enough to withstand the heat, it would be necessary to travel at the speed of light to escape. And, as far as we know, only photons themselves are capable of doing so.